Thanks a lot. Yeah, I would like to thank the organizing committee for inviting XRnanotech to this workshop. I learned a lot about vortex beams and the interactions of these beams with matter and quantum matter. I'd like to say that my talk is probably more simple-minded. It's an industry talk and probably a bit more brief. Nonetheless, I would like to convey the take-home message that XRnanotech can be a trusted partner for the fabrication of vortex beam devices or components. So to start off, I would like to introduce the company a little bit, then tell about our core technologies, show you a couple of examples, and then show two recent projects where we've worked on vortex beam devices. So most people who know us, or collaborators or clients, they know us in terms of X-ray optical components and systems. And that's exactly where we come from. We are a spin-off from PSI, and the first components that we sold are Fresnel sun plates. But in the last 2 years, we have grown. Now we also work on metamaterials and neutron optical components. So in a sense, you can think of us in terms of manufacturer of micro and nano components with specific in-depth application knowledge. About the company itself, so last year in 2024, we partnered up with Microworks. Microworks is a German-based company based in Karlsruhe. At the beginning, it used to be a spin-off from KIT. So we partnered up with Microworks to enlarge our technology and fabrication capabilities. The company itself comprises about 30 people working at both sites, at Villingen and at Karlsruhe. And the team itself is quite diverse. So I would say from the point of view of education, we have scientists, engineers, and technicians from different fields. And also in terms of, let's say, cultural history, we have about 10 plus nationalities within these 30 people at XRnanotech. Then our vision or mission is to innovate products covering nanostructures and optics. To do so, we often write grants, collaborate with industry, collaborate with academia, and with research institutes. And one point I would like to stress, even though we're growing quite fast at the moment, we would like to remain a flexible fab for rapid prototyping for micro and nano components. So what are the core technologies? We could differentiate these technologies into 3 different baskets. So we have direct write lithography, of which e-beam lithography and laser lithography are part of. Then we have 3D printing, aka 2-photon polymerization. And then we have LIGA. LIGA is an X-ray indirect lithography technique in combination with electroplating. So when we use e-beam lithography or laser lithography, we often have a workpiece or a substrate on top of which a resist is coated. A resist is a chemically active substance that is susceptible to the electron beam or susceptible to the laser beam. Whenever we need very small features, let's say 10 nanometers or more, we go for the electron beam because there we can get really down, we can really get these small features. It has good stitching, which means that when we pattern structures, there are no offsets in between. It's really nice stitched. The writing times are a bit longer. There are some charging effects, which I will tell you about in a later slide. And the structures that we can write with electron beam can be about 4 microns in height. So if the feature size is a bit more relaxed, so if you can have features of 500 nanometers and more, you go for direct write laser lithography. It's, again, we have good stitching, the writing is faster, you do not have any charging effects, and we can go up to 100 microns in height for the structures. If there's something in between, and if we have good use cases, so for feature sizes of 150 nanometers and more, we could use 3D printing, which in this sense means that we have a UV sensitive negative resist, and wherever the resist is in contact with the laser light, it stays, it remains, and we can wash out the rest of the resist afterwards. And one important thing is that with the 3D printing, we can actually fabricate true 3D structures, or not just 2 or 2.5D structures. that are only possible with E-beam or laser lithography. And in the end, there is this LIGA process, which is carried out at Karlsruhe. For that, we need a synchrotron, and we need a gold mask. In this way, it's an indirect technique. And therefore, let's say the writing times are a bit slow because you have to apply for beam time. But we can build structures up to 1,000 microns in height. So we can get really high aspect ratios. So let's move on to a specific example. How would we fabricate a Fresnel zone plate, or let's say binary phase Fresnel zone plate? So binary because we only have 2 levels. It's transmissive, and we do have some material. And phase because we often choose the material and the height of the material such that we get a pi phase shift to optimize the efficiency. We can also make the example a bit more specific, and let's say we want a zone plate with an outermost diameter of about 20 nanometers, and which is optimized for 5 keV incident beam. For that, we would use electron beam lithography in combination with gold electroplating. And here we have our substrate, on top of which there is a small chromium layer for better adhesion to gold, and then we spin a resist on top of it, which will be exposed with the electron beam. It's a positive resist, which means that when we develop this chemical or the resist, wherever we had electrons, it will be removed. And in this way, we get a mask for the electron plating bath, where we plate gold up to the height we predetermined. And in the end, we can remove the resist and get a binary phase Fresnel zone plate. Which is not shown here is that before we do that, we always calculate the ideal height for specific energies. And also, when we fabricate these zone plates, we usually work on multiple chips simultaneously to optimize the writing strategies. With writing strategies, I mean the dose of the electron beam and the biases. Another example is a blazed reflective X-ray grating. Here I would like to stress that this is a project in combination with the LEAPS consortium and carried out with PSI. There's also patent pending, the holder of which is PSI. That being said, I would like to draw your attention on the word grayscale, electron beam lithography. Grayscale means that we change the dose of the electron beam in a more continuous way. So in the previous example, we had a dose which was on or off. In this case, which is shown with these arrows, the dose is varied when we change the position of the sample. And to produce a reflective X-ray grating, we would do similar things as I've shown you before. We would have like a silicon substrate, would spin coat a negative tone resist, make a grayscale exposition, where then this HSQ resist is converted into silicon dioxide or silicon oxide, which is something that cannot be washed away when we develop it. And in the end, when we would like to transfer the structure into the oxide, we can do a thermal oxidation step. And this works because wherever we have more resist, the oxidation is slower, and wherever we have less resist, the oxidation is faster. And in this way, we can transfer the resist pattern into the silicon substrate. So this specific grating is used at the resonant inelastic X-ray beamline as an analyzer grating. And there's one more important step I would like to say, that we can get really smooth surfaces by further oxide removal. And therefore, we get these really shiny gratings. Now I would like to open the perspective a little bit and tell you where we do most of our work and what other capabilities we do have. So we work at PSI. We have access to the newly established clean room PICO, which is a class 10 ISO 4 clean room, which features about 1,000 square meters of lab space and equipment. And we have access to all the tools and chemistry. So besides the lithography techniques I've shown you before, the E-beam, the optical lithography, and LIGA, we are experts in electroplating of gold and nickel. We would also be happy to try new plating baths for different materials. We also do have protocols to deposit chromium, ruthenium, molybdenum, and aluminum. And we also have process engineers that are expert in etching and in wet chemistry, so we can etch silicon, silicon dioxide, and diamond. And I would like to just open a tangent that all the optics that we produce in gold or nickel, we can mostly produce in diamond as well, which is quite important for XFEL applications where we have radiation heating and radiation damage. One more important thing I would like to mention is whenever we don't have expert know-how, we seek collaborations with partners within Switzerland or within Europe. And now we just build up a new collaboration with a company in Marseille for nanoprint lithography of metal oxides. This is, for instance, for us quite important to fabricate metal lenses using titanium dioxide. Here you see one of our process engineers at the optical laser lithography station, and this is the wet chemistry in the background, and there is UV lithography. Along these lines, I would like to briefly mention how to best work with us. So usually there is initial contact through a web-based inquiry or through direct contacting, followed by a consulting phase, which is really the phase I like the most because we can go into the feasibility, into the materials, the design, the lead times, and also discuss the project type. If it's something we could do right away, it's an offer. If we think it's something we need development, it's an R&D project. And in this way, we can mitigate lead times and the way we work with clients, collaborators, or partners. Then the implementation phase really depends on the project type. If it's an order, it's fast. If it's an R&D project, we usually work on modules or on work packages and go from there. At the end, everything that we deliver will be inspected. There is a quality control through metrology, so it could be AFM, it could be SEM, it could be laser profiling, whatever is required for your specific metrology. And I also would like to mention that we do operate worldwide. We have representatives in Japan, we have a distributor in China, and with the company in Germany, we have another subsidiary in Europe. And we would like to expand towards the States next year with another representative. So what about Vortex Optics? I would like to show you two examples that we worked on recently. You know that's spiral Fresnel zone plates. We have seen that many times before. And here we worked on, together with the diamond light source for the beam time or end station IO5. In this case, we chose the contrast material to be silicon, where we etched a silicon membrane 400 nanometers in depth. The diameter of the zone plate was about 1.3 microns, and the outermost zone width was 200 nanometers. And we fabricated three different types, so orbital angular momentum with -1, with 0, and with +1. And the bright spot you see here in the middle is a gold beam stop, which is directly on the chip, so which is quite nice. You don't have to align your optics, so it's on the chip itself. And if it doesn't fit on the chip, we now have capabilities to bond multiple chips together through another collaboration at PSI. There's another project, maybe one. Oh, I am too fast. I would like to quickly say something about the substrates and the membranes that we use. So quite often when I talk about chips or membranes or silicon frames, what I mean is there is a chip where we usually have a solid silicon substrate, and on top of which there is a thin silicon nitride membrane or a silicon carbide membrane or a silicon membrane, which can have thicknesses from 50 nanometers up to 1 micron, depending on the incident X-rays. Also, the chip size can be 9 by 9, 6 by 6, 3 by 3 millimeters, and we can also adjust the window size to whatever our customer needs. And to the right, there is a wafer showing you these windows for specific geometry. So another project which I like a lot, we fabricated fork neutron gratings for the University of Buffalo for Dusan Saranac. We fabricated OM gratings with orbital angular momentum states 0, 1, 2, and 3. In this image, only the gratings with orbital angular momentum 3 are shown. So we have to the left, these are both side views. What's quite interesting here is that the materials, again, silicon, the height is 5 microns. The area is about 5 by 5 millimeters, but the pitch is 100 nanometers, which is quite, it's a bit crazy because you have a huge aspect ratio with a 100 nanometer pitch and a height of 5 microns. And maybe you wonder how we achieve this. So there's a nice technique called mag etch, which is metal-assisted chemical etching, which is ideally suited to achieve high aspect ratios in silicon. So how we do that? We usually have, again, like a silicon substrate where we physically vapor deposit platinum. Then we make a resist coating, expose it with the E-beam or with the laser beam, develop it. In another step, we can use argon ion milling to open up the platinum, remove the resist, and in the end, we get a platinum mask for a HF vapor bath. Wherever you have platinum, then the silicon is etched to the ground. And this way, we can get very high gratings that we can use for neutron scattering, or we could also use these structures to fill them with nanoparticles or microparticles. And we can really get very high structures. That is something I would like to show here. These are nanopillars or nanowires that are in 44 microns in height and have a diameter of about 100 nanometers, which is very extreme. So this way, I would like to conclude my presentation. Thank you for staying. And yeah, looking forward to questions.